So in this video, I will again discuss test at different level in verification. Test at different levels in verification. In hardware design, bugs can be appear different levels of complexity. To find and fix them efficiently, it is important to apply the right type of test at right level. Block level testing focuses on individual modules, usually designed by a single person. Example of bugs are really fails to add two number correctly, a bus transaction doesn't complete, a packet doesn't make it through, a switch component. Characteristic: easy to write, direct test, fast simulation time. Most bugs are self-contained. Let's see what this means. In block level testing, verification, the statement most bugs are self-contained the most means that most bugs are or errors in design tends to originate and man- manifest within the same module or block where the problem actually exists. What it is imply for block level verification? High bug detection efficiency. Since bugs are usually local to, to a block, through verification at the block level can catch a large portion of design issue early before integrating into top level system. Simpler debugging. Debugging is easier when bugs are self-contained because you can isolate them without having to trace signals through the entire design hierarchy. Importance of block level test bench. Writing robust and comprehensive test bench for individual blocks becomes crucial. If most bugs are local, then testing each blocks well means fewer surprises during system integration. Reduce integration risk by verifying each block th- thor- thoroughly and assume bugs are most internal. Integration becomes more about interface compatibility and less about deep logic failures. Encourage for module design. This principle encourage modular and hierarchical design practice, making verification more scalable and manageable. Takeaways in verification: assuming most bugs are self-contained supports the strategy of early focused and detailed block level testing because if you catch the bugs locally, you prevent their propagation and save time during the system level debug. So test bench must mimic surrounding logic, can be ca- can be code heavy. Integration level testing happens when multiple blocks are connected together. Issue often Issues often arise due to different interpretation of specification. Two designers interpret a protocol differently. One design of bus driver, another design the receiver. Their behavior doesn't align at the interface. Characteristic more realistic than block level. Blocks simulate each other reduce the test bench complexity, runs slower than the block level. Bugs are harder to trace, especially across the module boundaries. So this is in integration level testing. And then third is system level testing. The entire Dart design under test is simulated together. Goals is test how the blocks work together in real scenarios. Makes all the component active simultaneously. For example, an MP3 player plays music, user downloads songs, presses multiple buttons, tests real world scenario, multiple operation happens at once, detects data alignment issues, timing bugs, concurrent errors. Drawback: very slow simulations. Bugs analysis becomes complex and time-consuming. Error handling and robustness. Once normal functionality is verified, check how the design handle abnormal or faulty inputs. Error handling and robustness. Once normal functionality is verified, check how the design handles abnormal and faulty inputs. Techniques: error injection. Introduce a bad inputs or con- co- corrupt data. Check for partial transaction handling, recovery from errors, unaccepted control signal behavior. This often the hardest part of verification because it is taught to imagine all possible error. System level scenario and edge behavior. At system level, Correctness isn't just about functionality, it is about how multiple features interact. Example, an ATM router has to manage streams with different priorities. Choo- Choosing the next cell to transmit depends on the overall system behavior, not just local correctness. At system level, correctness isn't just about functionality, it is about how multiple features interact. An ATM router has to manage streams with different priority. Choosing the next cell to transmit depends on the overall system behavior, not just a, lo- a local correctness. Tips: use statistics and traffic analysis to check if aggregate behavior is correct. Use static and traffic analysis to check if the aggregate behavior is correct. Important notes: you can never be 100% sure that a design has no bugs left. Verification is an ongoing process. Keep creating new strategies to explore untested scenarios. Next, we'll see the verification plan and different and the verification plan uh, at a different levels. So in verification plan is your blueprint for testing design. Derivative form: the hardware specification contains list of features to test. What does the design needs to do? The testing techniques: example, direct test, manual scenarios, random test, automatic stimulus with constraints, assertions, auto check condition inside the design, HWSW co-verification, test both hardware and embedded software, emulation, runs tests on actual hardware instead of simulators, formal proofs, mathematical proof design behavior, verification IPs, VIP, reusable pre-built test component. Think of verification plan as a project map. It tells you that what to test, uh, how to test it, and when you are done. In summary, The block level is focuses on sing, single module or unit, and it is easy, fast, and bug localized. Integration level interface between multiple block it, and it can be a mismatched protocols. System level full design plus realistic use cases, and it can be complex and slow simulation. Error injection, which focuses on design robustness and fault recovery. It is hard but essential. Verification plan, testing strategy based on specification, and it has list features. It has features, list of features, techniques, and goals. Final thought. Final thought of this discussion. Start simple, then scale up to integration and system level testing. Always test both normal and abnormal behavior. Keep involving your verification plan with new tests and bug scenarios. Verification is never truly done, but good planning helps you get it closer. Next, we will discuss verification methodology manuals and the de- details of its, and then we'll see go to the basic test bench functionality. Thank you.